Bismillahirrahmanirrahim. Assalamu alaikum, dear students. This is our next problem. Problem having been chosen from the book Modern Physics by Kenneth S. Crane. This problem has two parts, A and B. Okay. So as usual, we first come to its statement. Part A. What is the reduced mass of the KCl, potassium chloride molecule? Okay. K stands for K and Cl stands for chlorine. So potassium and chlorine atoms, but their combined molecule is called potassium chloride. Okay. What is the reduced mass of the potassium chloride molecule? Part B. With an equilibrium separation of 0.267 nanometer, find the spacing of the transitions in the combined rotational vibrational spectrum. With an equilibrium separation of 0.267 nanometer. Dear students, here it is important to point out here that this value can also be seen or noticed from table of physical constants. Okay. So even if this value is not given in the statement, it can be found from the concerned tables. Okay. With an equilibrium separation of 0.267 nanometer, nano standing for 10 to power minus 9, find the spacing of the transitions in the combined rotational vibrational spectrum. Okay, combined rotational vibrational spectrum. In order to make this concept clear, we will introduce some helping tools. Okay. So as usual, now we move to our helping tools. Our helping tool number 1 is reduced mass of a diatomic molecule. Okay. Reduced mass of a diatomic molecule, Mr, where R is written as a subscript of M, is equal to M1 M2 over M1 plus M2, where M1 is the mass of atom number 1 and M2 is the mass of atom number 2. Okay, so reduced mass of a diatomic molecule, Mr, is equal to product of the masses of the atoms divided by the addition of the masses of the atoms. Okay, now we move to helping tool number 2. This helping tool is the table of atomic masses. Okay, table of atomic masses is usually given in almost every textbook of physics in appendix at the end of the book. Okay, dear students, table of atomic masses is very lengthy. It comprises several pages, about 8 to 10 pages. Okay. But here we have just taken a snapshot of 3 segments of this table. Okay, first segment contains hydrogen, information about hydrogen. Okay, the purpose of, while we have nothing to do with hydrogen, but this segment which consists of information about hydrogen ensures our continuity of this table. Okay. However, the second segment deals with potassium information, and third segment deals with the chlorine information. Okay, so we see about potassium, that is K. Okay, dear students, its mass number is 39. Okay, how we will fix this value? Actually, the reason is that 39 are in Decimal representation 38.963707 has been described as 93.26%. Okay, it's in this table abundance or half life is given. Okay, and where maximum percentage is given, we assume that that value is the mass number of this atom. Okay, so mass number of potassium K is 39. Okay, while its atomic number is 19. Okay, 19 and 39. Similarly, now we come to chlorine. Chlorine, this is 75.77, that is 34.968853, that is 35. Okay, its mass number is 35 and atomic number is 17. Okay, 17 and 35. Now we move to tool number 3. In tool number 3, two alternate versions of a table is are given. Okay, from this table we can see that potassium chloride, which is given in the last row in the lowest portion of this table, contains information that its dissolution energy in electron volt is 4 point dissociation. From this table we conclude that dissociation energy of potassium chloride is 4.43 electron volt, while its equilibrium separation is 0.267 nanometer. Okay, dear students, actually we do not need this table because this value is given in the statement, but despite this it is helpful to develop confidence that such things are also given in concerned tables. Okay, now this table has been repeated from some other book or from the same book at some other place in some different no, it is from some other book. Okay, table here once again, potassium chloride, this. Okay, 1 2 3 4 5 6. Okay, row number 6, potassium chloride. Its dissociation energy in electron volt is 4.43, while its equilibrium separation in nanometer is 0.267. Okay, so this table has been shown in its two alternate versions, and the purpose of this table is to ensure that value of equilibrium separation in nanometer is given in such tables. Okay, to helping tool number 4, this table has been used several times in our problems, in our videos. Dear students, from this table various values may be used. Okay, so this is a general table in which many values of physical constants have been enumerated, have been described, have been given. Okay, now we come to helping tool number 5. Okay, helping tool number 5. In this tool, rotational energies have been described. Okay, rotational energies EL, where L is written as a subscript of E. Okay, capital L is written as a subscript of capital E, and this it denotes rotational energy level. This is equal to L into L plus 1 H cut square over 2 mr equilibrium square is equal to B L plus 1. Okay, dear students, we can easily imagine, we can easily conclude that when L and L plus 1 is present in this expression, then B, capital B is equal to h cut square over 2m r equilibrium square. Okay, where dear students, h cut is actually Planck's constant divided by 2 pi. Okay, Planck's constant h divided by 2 pi is called h cut or h bar or h reduced. Okay, we also know that the value of pi is equivalent to 22 by 7, but this number is very special number and its decimal representation is non-terminating, non-repeating, it goes endlessly. However, we usually take the value of pi as up to 2 digit up to 2 decimal places as 3.14. Okay, so this is h cut is equal to Planck's constant divided by 2 pi over 2 into m is reduced mass and r equilibrium is equilibrium separation, which is not only given in the statement but also given in the two tables shown in helping tools. Okay, L starts from 0. Okay, L equal to 0, 1, 2, 3, 4, 5. Okay, as we put the value of L, we get rotational energy levels. Our alternate version of this expression has been given as EL is equal to this, where B is equal to this. Okay, no change. The only change is that here B separately has been shown as this equal to. Okay, now helping tool number 6. Vibrational spectra. The selection rule for transition between vibrational states is selection rule delta V is equal to plus minus 1. This is actually about spacing. Okay, a last part of this problem deals with spacing. Okay, similarly tool number 7, in this tool a figure has been shown, figure 9.31 expected sequences of absorption transitions between combined rotational and vibrational states. Each vertical line represents the absorption of a photon with a sharply defined energy 2b. Okay, so here our all emphasis is on the point that expected spacing is 2b. Okay, in order to justify this 2b, we have entered these two helping tools. Okay, helping tool number 6 and helping tool number 7. Okay, now dear students, we come to solution. Okay, solution. Let us calculate the reduced mass using the relation mr is equal to m1 m2 over m1 plus m2 of potassium chloride made with potassium 39 and chlorine 35 as reduced mass of potassium 39 chlorine 35 equal to mass of potassium 39 into mass of chlorine 35 over mass of chlorine 39 plus mass of potassium 39 plus mass of chlorine 35, and this alternatively becomes equal to 38.96 atomic mass unit U into 34.97 U. Okay, divided by 38.96 U plus 34.97 U. Okay, because dear students, in place of 39 and 35, its value in form of a decimal representation has been taken. Okay, which is which when rounded becomes equal to this value whole number. Okay, so a simplification of this will lead to 18.43 U, and we know that value of U as per helping tool, in which many physical constants have been included. According to that table, value of U is equal to 931.50 million electron volt over C square. Okay, so dear students, 18.43 into, in place of U we have used this value, its value from table. Okay, in the next value, in the next step, we have simplified these two multiplying factors, and it has become equal to this 1.72 into 10 raised to the power 4 million electron volt over C square, million electron volt over C square. Now we know that B is equal to H cut square over 2mR equilibrium square. Dear students, here H cut square is equal, H cut has become equal to 0.66 into 10 raised to the power minus 15 electron volt over second, electron volt into second square. So H cut value is equal to this within bracket, and H cut is appearing as a square, so it will also be taken in square. Actually, dear students, in table value of H cut is not given, value of Planck's constant H is given, and we have manually by ourselves divided that value by 6.28 2 pi. Okay, 6.28, and then the value has become equal to this, so it is in square, divided by 2 into reduced mass. This value which we have calculated earlier, we have placed this value into this value, actually dear students, here what we will do, here reduced mass is equal to this. Okay, and we have used this value in the next expression. Okay, but the problem is that this value can still be prolonged. How? Because at one place we can eliminate capital M, million, by using 10 raised to the power 6, and hence million will be eliminated. Moreover, we will have to eliminate C square. Okay, C square, C is equal to 2.998 into 10 raised to the power 8 meter per second. Okay, so we will also eliminate C square in terms of meter square per second square. Okay, so dear students, here that thing has been done. Okay, that is in B we have used the value of M, but after inserting value of M we have eliminated capital M by 10 by replacing it as equivalent to 10 raised to the power 6, and we have eliminated C square, speed of light, in terms of meter square per second square. Okay, and after substituting these values there is only simplification. Okay, actually exact I cannot point to point explain this simplification because some steps have been merged. Okay, anyhow, after simplification, value of B will become equal to this 15.988 into 10 raised to the power 6 electron volt, and this may be written as 1.59 into 10 raised to the power 5. Okay, because when we shift decimal one step behind, this power in minus will be reduced by 1. Okay, so B has become finally equal to this. This is our answer or solution. but we know that spacing is equal to 2b, so we will have to multiply it with 2 in, because after multiplying it with 2 we will go back to problem statement, and we will see what thing has been emphasized regarding spacing. Okay, we know that spacing is equal to 2b, and hence value of b has been found as this, so we will multiply this by 2, and hence spacing is equal to 2b is equal to 2 into, and hence it becomes equal to 3.18 into 10 raised to the power minus 5 electron volt. Now we move to problem statement. Okay, in order to ensure that something regarding spacing has been emphasized. Okay, dear students, this is with an equilibrium separation of this nanometer, find the spacing of the transitions in the combined rotational vibration spectrum. Okay, spacing of the transitions in the combined rotational vibrational spectrum, and for this purpose we have included two helping tools. Okay, we have already mentioned this thing, that two helping tools have been reserved for this point, and those helping tools are 6 and 7. Okay, 6 and 7 vibrational spectra. The selection rule for transitions between vibrational states is selection rule delta V is equal to plus minus 1. Helping tool number 7, figures expected sequences of absorption transitions between combined rotational and vibrational states. Each vertical line represents the absorption of a photon with a sharply defined energy. Okay, so 2b, we have to justify this 2b, which we have used in the last step of this problem. Okay, this is spacing equal to 2b equal to 2 into so, and this is equal to 3.18 into 10 raised to the power minus 5 electron volt, and hence this is the end of our problem. This is the end of our video. Till next video, Allah Hafiz.